Welcome to the Deep Dive, the show that takes the absolute deepest scientific research and synthesizes it into actionable, compelling knowledge for you.
Hey there.
Today, we are undertaking one of the most complex dives we've ever attempted. We're looking at the revolution happening right now in psychopharmacology.
Yeah, we're really going beyond the traditional white paper or the clinical trial. Our sources today merge some incredible cutting-edge AI analyzing millions of anonymous social media posts with these highly specialized mathematical models.
Right, to understand the fundamental mechanics of addiction and drug effects.
Exactly.
So our goal today is to tackle this massive intersection and really to boil it down to three essential takeaways for you. We're going to look first at how machine learning is tracking real-world drug effects through social media chatter.
Then we'll get into a pure quantitative model that tries to explain exactly how addiction develops in the brain.
And finally, we'll tackle the core ethical tightropes that clinicians have to walk every day when they prescribe these really powerful medications.
You know, this whole multifaceted approach is just so critical. The traditional system for monitoring drug effects, it's called pharmacovigilance.
Right.
It's inherently limited. Think about it. Structured reports from doctors and hospitals, they often miss experiences that are mild or highly subjective or, and this is the key, socially stigmatized.
So if a user has a bad but, say, manageable experience, they're probably not going to file a formal medical report.
No way.
Right.
But they are far more likely to tweet about it anonymously.
Okay, so we have to look at both at the same time. The broad, subjective, user-reported data, and then connect that to the deep underlying biological math. It's really the only way to get a complete picture.
It is. And what really stands out is how traditional systems, they just lag behind actual behavioral trends. If a new designer drug hits the streets, doctors might not hear about the subtle initial effects for months. Social media sees it instantly.
Okay, let's unpack this then, starting with how these researchers decided to treat Twitter, or X, I guess, as this unfiltered, real-time window into drug effects.
The initial scope was huge. They focused on 3 substances, ecstasy, GHB, and 2CB, and they collected over 6.7 million tweets.
6.7 million.
Over nearly a decade, yeah, from 2010 to 2019. But the challenge, of course, is that they weren't looking for clinical terms. They were hunting for slang, for informal narratives.
And they were trying to extract what they called phenotypic manifestations, which is just a very formal way of saying what did the user actually perceive? You know, was it a desired high or was it a toxic, undesired low?
Exactly. But that sheer volume, it makes manual labeling impossible. I mean, you can't hire enough people to read almost 7 million tweets and tag them reliably.
So they had to get creative.
They did. They turned to this fascinating strategy called weak supervision to automatically assign those preliminary, positive or negative labels.
Okay, walk me through how that weak supervision technique actually worked. It sounds like they needed a really high level of confidence in their labels, especially with all the noise you get on social media.
Right, so they used 2 parallel methods to sort of cross-validate the meaning. Method A was built on human intelligence, a curated list of slang terms that domain experts had already tagged as positive, negative, or, context-dependent.
And this is where you'd find some of the rougher terminology.
Oh, absolutely. For GHB, the keywords included terms like GEB, liquid ecstasy, and that truly sobering one, the date rape drug.
Wow. That's a sobering keyword to find in any data set, let alone social chatter. It just underscores why traditional reports often miss the severity of these darker effects.
It really does.
So what was the second method, the one that added the clinical rigor?
That's method B. It used a tool called MetaMap for biomedical concept extraction. The best way to think of MetaMap is like a super translator.
A translator.
Yeah, it takes the informal free text, like a tweet saying, feeling sick after taking this GEB, and it instantly cross-references that with structured concepts in the Unified Medical Language System, or UMLS.
Ah, so it's taking the wild world of Twitter slang and mapping it onto formal clinical vocabularies. It's standardizing the language.
Precisely. And here's the clever part. The researchers then only retained the tweets where the polarity positive or negative matched across both methods.
So the slang list and the MetaMap classification had to agree.
Both had to agree. And that final filter, that resulted in a much smaller but very high confidence data set of about 92,000 tweets.
And the findings from that refined data set were pretty striking, right? Especially the imbalance in the conversation.
Absolutely striking. First, ecstasy just dominated the discussion, making up over 83% of the mentions. But the polarity findings were extreme. A massive 95.41% of those tweets were labeled with negative polarity.
95% negative. Wow, that tells you a lot about the nature of public online discussion.
It does.
People aren't generally logging onto Twitter to file a report saying, just had a great day thanks to X, but they are posting when something goes wrong or they need help or they're just discussing the downsides.
And that's the bias inherent in the data. But for pharmacovigilance, it's actually a valuable bias. It highlights the toxic, undesirable effects that traditional reporting often misses.
But that 95% imbalance, that must have created a huge challenge for the machine learning models they wanted to train.
A huge challenge. If the model sees negative 95% of the time, it'll just learn to predict negative for everything.
And it'll still be right most of the time, essentially ignoring all the important positive or context-dependent cases.
Exactly. The algorithm just learns to cheat. So to fix this, they had to apply techniques to artificially balance the data set. One of the key methods was something called SMOTI.
SMOT.
Yeah, the synthetic minority oversampling technique.
Okay, so tell us why SMOT is needed here. What does it actually do?
Well, SMOTI essentially creates synthetic data points for the minority class, which in this case was the positive tweets. It doesn't just duplicate existing tweets. Instead, it looks at the features of the few positive tweets they have, and it generates new artificial data points that are similar but not identical. And that gives the AI model enough examples of a positive experience to actually learn what to look for instead of just defaulting to the negative label.
That artificial balancing that's ingenious. And once they addressed that imbalance, how accurate was the final model?
Extremely accurate. Ensemble methods, particularly one called extreme gradient boosting or XGBoost, it performed the best. It achieved an F1 score of 0.8668.
Which is a very high level of accuracy.
It is. It demonstrates that this approach can reliably support real-time pharmacovigilance, provided, and this is the key, provided they nail that essential step of handling the data imbalance.
So the big insight here is that social media, when you process it correctly and rigorously, it provides immediate, actionable public health intelligence that we just couldn't access before.
It's proof that we can monitor a population's collective experience in near real time.
Here's where it gets really interesting, though. Once we have the external data from millions of users, we have to ask, what does the internal wiring of addiction actually look like?
Right.
We're moving now from big data social trends to fundamental neurobiology, all analyzed through mathematics.
Yeah, the focus here is a unified dynamical systems model. It tries to map the core neurobiological basis of addiction, which is disruption to the dopamine system, onto three major psychiatric concepts. It's an attempt to quantify what we know about craving and tolerance.
Okay, lay out those three fundamental concepts for us.
So first you have the reward prediction error, or RPE. This is just the difference between the reward you expected to get and the reward you actually received.
So if you expected a great feeling and only got a moderate one, that's a negative RPE.
Exactly, and that negative RPE drives a change in behavior. Often, it means increasing the dose next time.
That makes perfect sense. It's the brain's constant recalibration mechanism. Okay, what's the second concept?
The second is the incentive salience theory, or IST. This theory basically says that drugs abnormally amplify desire. They hijack the brain's reward pathways, meaning the craving for the drug, the wanting, becomes disproportionately stronger than the pleasure you actually get from it.
The wanting overshadows the liking.
That's the perfect way to put it. And the third concept really defines the cycle of tolerance and withdrawal.
Which is the opponent process theory.
Yes, OPT. This is the physiological core of dependence. It states that every emotional experience is followed by a counteracting response from your body designed to restore homeostasis or balance.
And that's where the A process and B process come in, right? That's the foundation for tolerance. Tell us more about this dynamic.
So the initial drug consumption induces the quick, pleasant experience. That's the A process, the rush, or the euphoria. But that immediately triggers the body's counter-reaction, this unpleasant B process, which manifests as withdrawal symptoms and intense craving.
And I'm guessing this cycle just gets worse with use.
Precisely. With repeated use, the brain undergoes what's called neuroadaptation, things like the reduction of D2 dopamine receptors. This causes that negative B process to appear earlier, last longer, and become far more intense. The body is constantly bracing for the drug, and it just overshoots its compensatory response every time.
So the math here defines addiction not as some kind of moral failing, but as a predictable, self-perpetuating cycle.
It does. The model mathematically defines addiction as the state where the overall perceived reward, they call it bragging, becomes negative,
Yeah.
and the reward prediction error is persistently below a critical threshold.
Okay, can you translate that jargon for us?
Yeah, what that math means is that the drug has stopped providing any actual high wike is negative, but the user keeps taking it simply to stop the crushing, overwhelming withdrawal and negative feelings.
So it's not about pleasure seeking anymore, it's about pain avoidance.
That's the fundamental shift. And the model can even predict different pathways into that state. Some users decline steadily, monotonically, into dependence, but others show this damped oscillatory path.
The yo-yo effect.
The yo-yo effect, which is what clinicians see all the time. That cycle of temporary sobriety followed by a quick relapse. The user's RPE fluctuates. They might feel slightly better for a bit, but that long-lasting, strengthened negative B process eventually just drags them back across the threshold into permanent dependence.
But what is the absolute highest risk profile that's predicted by this purely mathematical framework? Who is most at risk?
This is the real nugget from this source. The model predicts that the users most at risk, the ones who transition fastest and deepest into addiction, are those who are genetically predisposed or neuroadaptively develop a stronger B process response.
A stronger B process response, meaning the negative effects, the withdrawal, the dysregulation, it's just more pronounced for them than for other users.
Yes, and this is so significant because of how it manifests in reality. It shows up as intensely severe negative affect and neuroticism. The source material notes this finding is consistent with clinical reports that neurotic individuals, people who manifest more pronounced negative emotional responses, are among the most at risk for addiction. Mathematically, they feel the pain of withdrawal more severely and for longer, which makes the motivation to use again just to neutralize that feeling that much stronger.
So if the math holds, treatments should really be focusing on lessening that B process.
And that's exactly what the model allows us to test structurally. It can study interventions like methadone for opioid addiction. Methadone acts as an auxiliary reward response, adding a positive component to alleviate that deeply negative, long-lasting B process, which can persist for days or even weeks after stopping the original drug. It's a mathematical solution to a neurobiological problem.
Okay, so we've analyzed the broad, real-time public data, and we've modeled the microscopic neurobiological dynamics. Now let's pivot entirely to the human element. The ethical decisions clinicians face when they're actually applying psychopharmacology.
Right. Psychopharmacology is the study of how medications affect the mind and behavior, focusing on neurotransmitters like dopamine and serotonin. And the ethical landscape here is just so complicated because clinicians are constantly balancing multiple core principles.
Autonomy, beneficence.
Right. Beneficence, which is doing good, non-maleficence, doing no harm, and justice.
And the central dilemma, it seems to me, is that doing good and doing no harm are often in direct conflict. You want to help, but every powerful drug carries risks.
That tension is acute, especially in complex clinical scenarios. I mean, consider the treatment of behavioral and psychological symptoms of dementia, or BPSD.
This would be treating things like agitation, aggression, or psychosis.
Exactly, and in patients who often lack the capacity for informed consent. Now, the standard of care is non-pharmacological interventions first, but when safety is threatened for the patient or for the caregiver, medications often become necessary.
And that's where the ethical calculus becomes, well, brutal.
It does, because many of the necessary antipsychotic medications carry significant risk. The FDA has issued a black box warning about the increased risk of stroke and mortality in persons with dementia. So the clinician is forced to weigh the immediate visible harm of aggression versus the long-term statistical risk of a stroke.
That puts the doctor between a rock and a hard place, especially when the family is involved.
Absolutely. The clinician might believe, purely under the principle of beneficence, that the patient needs this medication for their own comfort and safety. But they often have to negotiate with a surrogate decision maker, a family member, who, invoking respect for the patient's diminished autonomy, might just refuse treatment. That is an agonizing negotiation to have.
And moving beyond the clinical room, the economics of these treatments introduce their own dilemmas. Let's talk about affordability for a second. Is it ethically justifiable to prescribe a newer, maybe life-changing medication if you know the patient can't afford it long-term?
This brings up fundamental questions about justice. The source material emphasizes there's no simple answer here, but the clinician has to weigh that potential benefit against what could be devastating disappointment.
So how does a clinician justify it then, in the face of, almost certain long-term unavailability?
Well, one way to approach it in terms of beneficence is to prescribe a short trial period just to confirm it works. If the drug is wonderful, then the clinician has ethical justification to aggressively pursue every possible avenue grants, patient assistance programs, social services to get long-term access.
I see. So if you can confirm the life-changing benefit, it changes the weight of the moral argument.
It does, even if the eventual outcome is still uncertain.
That frames the decision not as an endpoint, but as a step in a really complex process. Let's address one final tension point: the influence of the pharmaceutical industry itself. The perennial question of whether physicians should accept small gifts like meals or supplies from pharma reps.
Yeah, there are long-standing, very legitimate concerns that these kinds of interests can introduce a subtle bias in medical decision-making, leading doctors to favor one brand over another.
But the consensus seems to be that it's not always a clear-cut no.
Right. The consensus finds that it is sometimes appropriate for physicians to accept these things because the visits themselves are often the most efficient way to learn about truly new treatments that could help their patients.
So it's a trade-off. It's balancing the avoidance of bias against making sure the patient has access to the most cutting-edge knowledge.
Precisely. If a new revolutionary drug is launched with a unique mechanism of action, the physician has an ethical duty to know about it. The challenge is just ensuring that knowledge transfer stays objective and doesn't cloud the final clinical judgment.
So what does this all mean? We've traced a path from millions of anonymous social media posts, filtered through complex AI, right down to the fundamental mathematical dynamics governing craving and neuroadaptation. And then finally, to the toughest ethical questions that play out daily in the clinic.
The synthesis is, I think, very clear. The future of psychopharmacology demands this dual perspective. We need the breadth of the broad, real-time public discourse for safety monitoring and identifying trends. And we need the precision of these individualized mathematical models to predict which users are most biologically vulnerable.
It's about leveraging these seemingly disparate fields to create interventions that are targeted, ethical, and actually effective.
And when we understand that addiction isn't just a behavior, but a predictable, self-perpetuating neuroadaptive process, the one governed by that strengthened painful B process, we move closer to real solutions.
Given that we now have the tools AI classifying millions of tweets and mathematical models that can identify high-risk profiles based on the strength of that negative B process response, it raises a really provocative final thought for you to consider. How could public health agencies use this combined data set, real-time social monitoring, fused with personalized mathematical risk profiles, to fundamentally change how addiction treatment resources are allocated in the future?